morning, everyone. Welcome to TCP injection attacks in the wild, a large-scale study. You are in the Mandalay Bay EF, and your speaker today is Gabby Nakibli. A few things before we begin. Stop by the business hall located in Bayside AB. The Black Hat Arsenal is on Palm Foyer on level 3, and of course the Arsenal reception is at 1700. If you haven't picked up your merchandise today is your last chance to visit the Black Hat Schwags and bookstore, and visit the Kali Linux lab on Mandalay Bay A. And thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick up. And without further ado, I present Gabby.
Hi everybody, thank you all for coming. Today I'm really excited to share with you some interesting results of a large-scale survey we've conducted in order to search and analyze TCP injection attacks in the wild. Throughout the study we have examined more than 1.5 petabits of web traffic coming in from web servers having in total 1.5 million unique IP addresses. To the best of our knowledge, this is the first large-scale internet survey of this scope that aims to study the practice of TCP injection attacks in the wild. What we wanted to do is to understand what kind of TCP injection attacks are currently going on in the wild, to what purpose, and who are the entities behind those injections. The collaborators in this research were Jamie Shkolnik and Yossi Rubin. Before we begin, just a quick introduction. Again, my name is Gabby Nakibli, and I'm a fellow at the National Lab in Israel, which is part of a larger company called Rafael. I'm also an adjunct lecturer and researcher at the Technion, and I spend most of my time doing network security research. Okay, so this is my agenda for the talk. First off, I will define exactly what is TCP injection and how we can identify TCP injections. Then I will touch on the networks we monitored, in which we identified those injections. Then I will explain, I will give you several examples of the TCP injections we have found and what purpose they served. And I will describe our attempt to identify the entities behind those injections. And finally, I will touch on a proposed client-side mitigation that aims to block those injections. Okay, so now let's start with the basics. What is exactly a TCP injection? A TCP injection is the event in which a third party adds to an existing TCP session a false packet. And the false packet is sent to either one of the peers of the TCP session as if it were a legitimate packet. In this study we focused only on HTTP session, on web traffic. And of course, TCP injection can only occur for unprotected traffic, so injection cannot occur for HTTPS. In addition, throughout our study, we've encountered practically all of the injections we encountered were done by on-path entities, meaning entities that has full control on the data path and can eavesdrop all the TCP, all the packets of the TCP session. Generally, they are an ISP, a government, or an attacker which compromised the router of an ISP or a government. Actually, throughout the presentation, I will show you an example of TCP injection attacks performed by all three of these entities. And we assume that injections are done out of band, meaning that the injector does not update or delete or drop the legitimate packets. Later on, I will explain why we need to assume that, and I will also explain why indeed this assumption holds in practice. TCP injections are generally not a new technique. As an attack technique, they are not new. TCP injection probably is as old as TCP itself. It has been reported in the past that it is used by ISPs to throttle peer-to-peer traffic on their network by simply injecting TCP reset messages. It is also used for censorship by injecting 404 or 403 HTTP responses. Actually, numerous injections we have found indeed are censorship related, and of course discuss them later. And according to the Snowden documents, we know that the NSA is heavily invested in TCP injection attacks. They call it the quantum operation, and they actually inject malicious payload in order to compromise the client's machine. So now let me walk you through a typical progression of a TCP injection attack. Let's say we have on the right a web server that is trying to deliver content to the client on the left, and we have an attacker on the network or an injector that tries to modify in some way the website delivered to the client. Now, for the sake of the example, let's say that the content it wishes to alter resides on the third packet the web server is about to send to the client. So we start by having the web server send the first, first couple of packets, and afterwards the attacker crafts a forged packet with the forged content. And the important thing here is that the sequence number, the TCP sequence number of the forged packet must have the same sequence number as that of the legitimate third packet the web server is about to send to the client. So it sends it off to the client, and of course the actual server sends the legitimate third packet himself. Now, according to our assumption, this is an out-of-band injection, so the third packet, the legitimate packet, will not be dropped by the injector. So what we have here is actually that the client will receive two packets with the same sequence number, and this is a race between the two packets. If the forged packet arrives to the client before the legitimate packet, then the forged bytes will be processed by the TCP stack and will be delivered to the browser, and the legitimate packet will simply be dropped by the TCP stack as an unnecessary retransmission. The TCP stack will see the legitimate packet and it will say, okay, I already got those bytes with the same sequence number, I don't need them, and it will throw it away. And the client will see the forged website. Of course, if for some reason the legitimate packet would win the race, then of course the injection will be unsuccessful. Now, this is where we've done our monitoring, right on the border router of the edge network, very close to the client. This is where we search for injections. And we identified injections by pretty straightforward. We simply identified pair of packets that are in a race, meaning two packets in the same session that have the same sequence number, but a different payload. This is a crucial thing, a different payload. And this event should not happen in normal TCP session at all. And if it does happen, if two packets having the same sequence number carry a different payload, then this is very indicative of a TCP injection attack. Now, as you can see here, we are able to identify a TCP injection simply because the injector did not drop the legitimate packet. This is why we can do it. So probably most of you now ask yourself, why the heck wouldn't the injector drop the legitimate packet? It would make our life a lot harder to identify those injections. And the answer is simply performance and reliability. Most of the injections we have found are done by network operators. And for a network operator to drop a packet, it needs to deploy a middle box that has some kind of a logic that decides which packets to pass and which packet to drop. It doesn't have to be a separate middle box, it could be an additional logic in an existing middle box. But this logic now presents an additional single point of failure in the network. Because if this logic fails for some reason because of a bug in the code, then the whole production traffic now stops. And if this logic now becomes loaded, then the whole production traffic of the network operator simply slows down. And network operators hate single point of failures and performance bottlenecks in their network. This is why they much prefer to do this kind of injection by simply out of band, by just placing a tap or port mirror that simply copies all the production traffic to the injector functionality, which decides when to inject the packet. And if this injector functionality fails or become loaded, then it doesn't interfere with the flow of the production traffic, and it is much less riskier for the network operator to do that. So this is why they prefer to do an injection out of band, and the legitimate packets do not get dropped. Okay, so these are the networks we monitored to search for injections. In total, we monitored the networks of 3 universities and 1 enterprise. I cannot reveal the actual details of the networks, but because we signed an NDA, but it doesn't really matter. The networks serviced more than 75,000 users, and as I said, in total we monitored more than 1.5 petabits of data, of web traffic. And this is the big table that summarizes all or most of the injections we have found. We partitioned the injections into 14 groups based on the injected resource. And here you can see in the table that this is the name of the group we've given, the destination site, meaning the site that was injected to, the site that the content of which was altered, the location of the site. And here you can see that the majority of the sites reside within China, and this gives you the first clue that the entities that inject the traffic and do the TCP injection actually are Chinese injectors. This is the short description of the injected resource and the purpose. 8 out of the 14 injection groups had the purpose to inject advertisement, to add an advertisement to the website. Of course, this is in order to increase the revenue of the injector to make more money by injecting the advertisement. 4 of the groups had distinct indications of malicious intent to compromise the client, and 2 of them had aimed to block content, but they were not censorship related. There were other injections we have found that were censorship related, and I will talk about them later on. So first, let's talk about the ad injection. This is a snapshot of the Apple's website taken a few years ago before we did our research. And what's wrong with this picture? The advertisement. Yes, of course, the advertisement at the bottom. This is not organic to the web page. This advertisement was injected a few years ago by an American ISP to all its customers. It is called CMA Communications. And actually, over the past few years, several ISPs have been identified to inject advertisement to their customers. And the thing is that in all of those instances, the ISP which injected advertisement was always the edge ISP, meaning the ISP that was closest to the client. It was his first hop to the internet. And let me just illustrate this for you. Again, we have on the right a web server, and on the left a whole bunch of clients that are serviced by different edge ISPs. And let's say that one of them is an injector that wishes to inject advertisement. So that means that only the users that are serviced by that edge ISP will see the advertisement, and of course all the other users will not see the advertisement. So in general, up until our work, it has been general assumption that only edge ISPs inject advertisement. In this work, we are the first to notice that also non-edge ISPs also inject advertisement, and this is much more serious because now they can inject advertisement to all internet users because they simply control all the traffic coming out of the web server. So here is one of those injections. Here you can see here the user simply browsed to a website called tfkp.com, just doesn't really matter. And the website referred the user to a resource at cnzz.com. cnzz.com is a Chinese service that tracks user statistics, much like Google Analytics. So I assume that many websites in China uses this service. So this is the request to cnzz.com, and in response to that request, the user got two responses. The left one is the valid response from the actual website, from cnzz.com. Here you can see just there is a JavaScript code, and the right one is the injected response, injected somewhere along between the server and the client. And this is simply a redirection, a 302 redirection to another JavaScript code named google.js. It's located at the domain 899j.com. Now, after we analyze this JavaScript, we've seen that this JavaScript simply redirects the user through an affiliate ad networks until it reaches the Google's ad networks, and then the user is simply served with an advertisement. And probably, of course, the injector had some sort of a gain from this injection. Probably he got revenue sharing with this affiliate ad network. Yet another example of an advertisement injection is for a user who browsed jihadist.com, which is a Chinese company that provides social sharing toolbar. Again, on the left, the valid response, and on the right, the forged response. And this time, also redirection, but this time using the HTTP's meta tag refresh, which simply redirects the user to the URL you see down below. And this time, the user was redirected to Baidu.com, the Chinese search engine, with the search term Uniqlo, the fashion store. And simply here the user was served with all the search results for Uniqlo. And of course, the injector did not forget to add to the URL the referral tag, as you can see here, right here. This is actually allows the Baidu.com to identify which site referred the user to make that search, and this actually allows for revenue sharing between Baidu.com and the site that referred the user. So this is, again, as you can see, the injector made money out of it. Yet another example here now, there's not really a redirection, but simply the injected response added a JavaScript code, which simply pops out an image, as you can see right here, and it prompts the user to download an executable. At first, we thought that the executable was malicious, but after we looked at it, it seems like a legitimate antivirus called Kingsoft Security. Okay, so up until now, you've seen only examples of injections of advertisements, but there were also injections that had malicious intent, like one of these. In this injection, an Android device tried to download an APK from a third-party website, and the user got a forged response, again, a 302 redirection to download the APK from yet another IP address. According to the Bot Scout service, this IP address is flagged as a bot. And once we retrieved the alternative APK, we found out that it was actually flagged as by an antivirus as a malicious payload. It was a well-known Android Trojan. So actually what happened here is that the user tried to download an APK from some website, and it was silently redirected to another site to download a malicious APK. Yet another injection, this time for an American website, actually victimized the users of many gambling sites, all from a single vantage point. And this injection targeted the website gpwa.org. GPWA is the acronym of Gambling Portal Webmasters Association. This is the association of the website administrators of gambling sites. Apparently there is such an association. And this association runs a certification program, and every gambling site that meets this certification program, it gets approved by GPWA, and it gets to show a seal on its website that brags that GPWA approved the site. There's nearly 2,500 gambling sites that are approved by GPWA. One of them, for example, is onlinecasinicity.com, which, as you can see at the bottom, shows the GPWA seal. Now, interestingly enough, in many of the sites, this seal is saved as a resource, not locally in the site, but remotely on gpwa.org. This means that every user that, for example, views onlinecasinicity.com will be referred also to gpwa.org to fetch the resource. For example, this is a request for such a resource. This is for another website called EuropeanSoccerStatistics.com, another website that is approved by GPWA. And the injected response, the forged response the user got, is actually JavaScript. Which, as you can see here, the JavaScript on the right simply redirects the user to another JavaScript, but this time it is located at the domain qpwa.org, which is suspiciously similar to gpwa.org. And QPWA is registered under a Romanian citizen, which is not affiliated to GPWA, and probably just it is just a bogus identity. And actually, we learned that this injection only happens for once for every IP address, meaning that if there was an injection to a client, the client will not get injected again. And actually, if you can read this JavaScript, you will see that the JavaScript will not run twice on the same machine. So here the attacker was very careful not to run his malicious code twice on the same machine. Unfortunately, we couldn't retrieve the actual malicious JavaScript, but we talked to the GPWA folks, and we learned that probably what happened is that the attacker actually compromised one of the routers of their ISP and simply injected this forged response to all their users. And actually, okay, and probably what happened here is that the attacker compromised the client's browser. According to the GPWA folks, the only intention was to add the advertisement and the spoof affiliate tags. But probably my guess is that because the attack is so sophisticated, the attacker had to compromise the router and do all these injections. Probably it has greater ambitions, but I can't really know. So all the injections I've shown you so far were actually commercially motivated, both the advertisement injection and the malicious injections. All of them were serving the injector to make more money. There are another category of injections which are politically motivated and not financially motivated, which aim to do censorship. So indeed we encountered numerous injections of censorship. All of them are by the Chinese government. And most of them look pretty much like this. They had the forbidden response code, 403, and this response body. We simply just show the user a laconic message that says due to laws and regulations, the site cannot be shown to the user. Now, the interesting thing here is that we monitored networks outside of China, which means that the Chinese government actually blocked users outside of China from accessing content within China. And this is in contradiction to the classic censorship in which the government blocks content of Chinese users, block Chinese users from seeing content outside of China. So here we learned that the Chinese government not only censors Chinese citizens, but also users outside of China, which is interesting. Now, in the next step, we try to reproduce the injections. I will let you know that for each injection group, we only seen it, the injections of each injection group, we will only encounter it for just a short period of time, just a day or two. Afterwards, the injections of that same injection group were not encountered. So we tried to reproduce those injections again. We simply tried to send the original HTTP request that triggered the original injection we observed. And here are the results. Big fat nothing. None of the injections we were able to reproduce, simply zero. And this was actually a big disappointment. But after the initial publication of this work, came to the rescue a researcher named Eric Helvig, as you probably, or some of you may know him as the author of the popular network miner, and he also tried to reproduce the injections, and he was more successful than we are. He managed to reproduce 2 of the injection groups out of the 14. But after a few weeks, he also didn't manage to reproduce those injections too. So from all this, we come to the conclusion that probably commercially motivated injections are perhaps transient in nature. By the way, the censorship injections, we were able to reproduce all the time, but this was less interesting for us because we knew that the Chinese government was involved. We wanted to reproduce the commercial injections. So probably those injections are transient in nature, meaning that the injector targets a certain website just for a day or two before it moves on to other websites. And this is probably just to be under the radar and to not draw too much attention. Maybe for a day or two the users will not notice the injection, or the site administrator will not spend too much effort to investigate this injection. So now we turned our attention to find out what is the identity of the actual injectors behind those injections. First, we tried, of course, to identify those injectors, but quickly we realized that it was nearly impossible because there is not really any identified information inside the injected payload. So actually what we tried to do is identify the location of the injectors, from which network the injected packet was triggered. And more specifically, we tried to identify the autonomous system from which the injected packet was triggered. By identifying the autonomous system, we can identify the entity that is responsible to the infrastructure from which the injected packet was triggered. And now I remind you that all the injections were performed on path, meaning that the injector had access to the infrastructure, so the entity that is responsible to that infrastructure has to be responsible for the injections. To do that, we used a simple heuristic based on the TTL value in the IP header of the injected packet. And in this we leverage the common insight that initial TTL values are usually have 4 distinct values. Most commonly they are either 32, 64, 128, or 255. This is the most common values for initial TTL. Values set by the operating system. For example, I think Linux, most flavors of Linux set the initial TTL value of their IP packets to 64, I think. And maybe Windows 255, but I don't really remember. But this is the most common values. So actually what we tried to do is, based on these common values, to estimate the number of hops the injected packets traverse. For example, if we see an injected packet with a TTL value of 59, then most probably the initial TTL value of that packet was 64. It cannot be 32. And it probably is not 128 or 255 because these values are too high. So it most probably was 64. Then most probably the injected packet simply traversed 5 hops along the path. And if we actually know the path between the server, the injected web server, and the client, and we assume that the injected packet was triggered along the path from the server to the client, so we can simply pinpoint the location of the injector by simply just counting the number of hops from the client back to towards the server. And in this case, the 5th hop from the client actually gives us the location of the injection. And these are the results of our analysis. As you can see here, in most of the injections, we've seen that the injector resides only between 2 to 5 hops away from the actual website that was injected, pretty close to the actual website. In all the cases, the injector resided within the autonomous system of the website, which is, if you think about it, it's pretty makes sense because the injector would like to sit as close to the web server as possible. And as you can see at the table, okay, it went out. Okay. As you can see here at the table on the bottom, these are the entities that are responsible for the ISPs that are responsible to this autonomous system. And as you can see here, the two ISPs were responsible for the majority of the injections: China Unicom and China Telecom, which are perhaps the largest ISPs in China and all of Asia. And we are not certain that these actually were. These entities are, these entities are actually responsible, the direct cause for these injections, but they own the infrastructure, and we know that the injector sits on the infrastructure, so probably they are. The US ISP, Information Technology Systems, related to the GPWA case, and we know that this ISP was not responsible for the injection because the attacker simply compromised one of its routers. So for the last few minutes, I would like to touch on the mitigations of the injections. The best mitigation here is simply using HTTPS. If the TCP packets are authenticated, then they the injection cannot happen. Unfortunately, still many websites do not support HTTPS, so we wanted to now search for another mitigation which is dependent only on the client and allows it to block injections even if it cannot use HTTPS. So the naive approach here can be, for example, just search for REST packets on the incoming traffic to the client, exactly the same way as we did in our monitoring system, but just do it on the client. And but this only allows to detect the injection. In order to block the injection, we need actually to delay each and every packet for, say, like 200 milliseconds in order to make sure that the current packet do not have other packets that are racing it. Only after 200 milliseconds that we do not detect a race can we let the packet pass. And 200 milliseconds per packet builds up to a lot of delay. It substantially increases the load time. So actually an improved approach might leverage an insight we had while we investigated the injected packets. In almost all of the injected packets we have seen, the IP ID and the TTL values in the IP header of the injected packet had abnormal values, meaning they were not in sync with the TTL values and the IP ID of all the other packets in the injected TCP session. So we actually can leverage this by simply just delaying only the packets that show abnormal values of IP ID and TTL, and only for those packets search for erase. This allows us to delay only a very small fraction of the packets. Of course, this is a big but here, there is, if the injector tries to mimic the same IP ID and TTL values as that of the legitimate packets of the TCP session, then of course it will not work. And this mitigation would not work. But still, at least the injections we've found, we've shown that, we've seen that all of the injections, the injector simply do not try to mimic the IPRD and TTL values. So these are the results. So we did a small experiment on benign traffic that has no injections, and on all the injected sessions we found. And indeed, the naive approach, as we expected, substantially increases the load time of the web page. However, the improved approach, which delays only the packets with the abnormal TTL or IPID value, had a much moderate increase, but it is on the expense of some missed injections. Again, injections that were their IPID or TTL value were not that different from the legitimate values of the other packets in the TCP session. Okay, so with that, I would like to conclude with the black hat soundbites. So these are my soundbites. The main takeaway from the presentation: TCP injection is a powerful technique that is deployed currently on the internet by ISPs, government, and attackers. We learned that Chinese ISPs add rogue advertisements to websites accessed by all internet users, not only the Chinese users. And when possible, use your IDS to detect those injections. As you've seen, detection of injections is pretty straightforward. And if you want to block those injections, you can use our proposed method. And finally, we published samples of those injections. So if you are interested and you want to dig in, you are very welcome to do so. And here's the link, and the link is also in the white paper that will be published. So with that, I would like to thank you very much. And if you have any other questions, I will be happy to answer. Thank you. Okay. Yes, please. Yes. How the hackers guess the TCP sequence? This is because they are at the on path and actually can see the TCP sequence number of the legitimate TCP session. So they don't have to guess, they simply see it. Okay? Observe the sequence numbers. Yeah.
Doesn't the point vector be aware of the content it's overriding?
Yes, the injector is always aware beforehand of the actual content of the original website. It does its homework. It knows exactly what it wants to inject and what is the original content and where it should be injected. So the injector is well prepared for this.